Okay, today our plan is three things. Number one, I want to show you a new element, the 2D elements. Just an intro, brief introduction to 2D elements. Okay, don't worry, you will not be tested on next week. Okay, on 2D elements. Then I want to spend some time to review the what we've learned so far, and somehow what you expect in the midterm exam next week. And number three, I like to learn and get some information about the progress of answers. What have you done so far? Because after the midterm exam, you have a lot to catch up. You owe me some labs. I want to see them. Okay. So, yep, let's do some work. Okay, 2D elements. What does it look like? It's a triangle. Okay, but do not confuse this triangle as a free truss element. This element, the triangle, the 2D element is a solid wedge. Okay, the whole thing is solid and it has a thickness as well. Okay, the one with three truss elements. If you see that in the problem, I'll show you. It's constructed of 3 string elements. Okay, it's very obvious. Okay, so this solid elements, 2D elements, right, has 3 nodes. It's one element only with 3 nodes. And the 3 nodes can be identified with a coordinate. If this node is I, this node is J, K, then the name of this node can be identified by the coordinates xi and yi. X, K, Y, K. X, J, and Y, J. So each node has a name, IJK, and each node has an address. Okay, very important. That's it. And then each node is allowed to move because, well, remember, it's finite element is all about string energy. You deform something, everything is the energy is stored within the string energy of the system of the elements, right? Each node is allowed to move 2 ways. Anything moving along the x-axis is identified as a u. So the movement on J node will be uj and vj. How you name it doesn't matter, but usually this is how I do it. Anything moving along x, I call it u. Anything moving along y, I call it v. U, k, and v, k. So this is one element, 3 nodes. But how many degrees of freedom? 6. Okay. Now here's the displacement vector. Ui, vi, u, j, v, j, and u, k, v, k. Any questions so far? You guys still here? All gone?
Chris, sorry. Could you please just explain the degrees of freedom again? How do we find them, I mean?
Degrees of freedom?
Yes, please.
Is how degrees of freedom is how much it can, which every element has some sort of degrees of freedom. How much it can move, what does, okay, review. The string element, okay, like draw it right here, string element, 2 nodes, but each node only allowed to move one direction or that direction. But so the node has 2 degrees of freedom.
Okay.
Okay, and then the trust element, right? Each node can move X and Y. So the trust element has 4 degrees of freedom. Okay, don't worry, after the 2D elements, I'm going to review every single tab we went through over the course, and I'll tell you more about the degrees of freedom. Yeah, hold on to your questions, but for now, 2D elements, 1 element, 6 degrees of freedom, which is UI, VI, UJ, VJ, UK, and VK. I heard there was another question before, like someone's, like any more questions before I move on? You must understand this, very important. Each element, how many degrees of freedom?
I was just gonna ask, for the 2D element, can the forces be anywhere on the element, or does it have to be at a node?
I'll talk about that later, yes. But when I apply the force, I can apply it anywhere on the elements, yes, but you have to transform that. Let's say I apply the force right here. I have to transform that force into the three other nodes. Because each node is kind of a sensor. It's able to receive information, receive a force, and also it tells you how the node displays due to that force. So the node has 6 degrees of freedom. It's able to receive 6 forces, and also it tells you 6 displacement. Okay, the displacement, you may log them, and you may detect how it moves due to that some force. And let's say if I apply some force within the elements in the middle, we need some equations. Translate that force in the center to 3 nodes first before we carry on. Vice versa, you let's say you have some movement on the 3 nodes, and then with that 3 movement on each node, you are able to tell the exact movement within the center of the element. But you kind of jumping ahead, very soon I'll show you how I do it. Good question. Yeah. Okay, and I promise I'll tell you more about degrees of freedom later. Okay, so after this, we have identified a displacement vector. Then what? Every time we want to develop an element, we want to find out the stiffness matrix, right? And the first step to find this kind of first step is look after the shape function, right? Okay, which is that's displacement of u, the horizontal displacement in any coordinate, x, y. I assume 3 constant. And then any displacement in the y directions in any coordinate, I assume 3 other constant. Okay, so far so good. Then this is what we assume, right? And we know exactly what's going on in I. in I, okay, xi plus a3 yi. At xi and yi, the movement along u is ui. X, the vertical displacement in node I, okay, is a4, a5, xi, a3, y. Oh, sorry, it's a6, y, I equal to vertical displacement on I. We do the same thing with xj, yj, and xk, yk. Okay, lots of writings. I'm being lazy, and I don't want you guys out of patience as well. So I refer to the note. This is what I did. I just substitute xi, yi, xj, yj, xk, yk into the equation. I get the result. Okay, that's it. Just like what we did in the beam element and the minimum potential energy section, we factor out all the constant A1, A2, A3, A4, A5, A6. Okay, we get this ugly term. We want to evaluate the constant A1, 2, 3, A4, 5, 6, right? So we inverse that. And put it on the other side. And you get like two very, very ugly terms. Each one, the 3x3 matrix is a 3x3 matrix. And each term has its regular numbers. Each term can be evaluated by the coordinates. This is all coordinates, okay? And the area, 2a, the area is the area of the triangle. You may calculate the area just by itself. Well, we all know how to calculate the area of the triangle, right? Or you may use the Excel spreadsheet to calculate that. Okay, I won't assign this homework to you this week because I want you to study the midterm exam. But the week after, I want you guys to design an Excel spreadsheet. So what it does, the Excel spreadsheet is you will need that for your final exam as well. The input is the coordinate. The input is the coordinate of 3 nodes, okay? After you input that, the Excel spreadsheet will calculate the alpha, beta, and I think this is a delta for you, okay? Anyways, today is a brief introduction to 2D elements only, but next week I will tell you more about it and then tell you more about the assignment, okay?
So next week we're gonna have the midterm and the class.
Oh, sorry, no, don't worry, my fault. Okay, the week after, Next week, don't worry, man, only midterm only. Okay, I'll tell you more information about it, but I'm just saying in the future, I want you to design Excel spreadsheet for 2D element to calculate the alpha, beta, and delta. Okay, where were we? That's right, we have A A1, A2, and A3 is that big terms right here. And then we factor out the UI, UJ, and UK, just like what we did in the previous sessions. We get a shape function for 2D elements. Look at that, you know, well, it's really painful to do all the alpha, beta, and beta by hand. So that's why you need an Excel spreadsheet to calculate that. And the shape function can be expressed by alpha, beta, and delta, as long as you have a coordinate. Okay, what we had right there is we have a equations for horizontal movement. That thing tells you up and right, left or right, and V tells you anything on a up and down. But it's a 2D elements. We want to merge them together, right? So here you go. Look at that. This is the displacement vector that we defined at the beginning of the class. Still there. And then you use the we rewrite the shape function 2 times. With that shape function, what's the next step? We need a displacement and string relationship. Okay, watch out. What we did before, what we did previously is all in one dimension. Okay, the spring elements is moving only X directions. If I put the spring elements vertically, it's so stupid. It only goes up and down or left or right. The truss elements, you can do like a X and Y along the spring elements, along the truss. Okay, it moves X and Y, but it doesn't study the relationship. Okay, when you squeeze something on the X direction, it doesn't change anything on the Y because it's 1D. But we in these 2D elements, right? Every time we squeeze something, or we stretch something. I stretch this, the thing become longer. At the same time, it goes thinner. Okay, if I squeeze it, compress it, it goes shorter and a bit wider as well. This term is called a Poisson ratio. Okay, so any movement in any movement in the X direction is going to change something in the Y. And any changes on the vertical directions, it's either getting wider or thinner. And again, I will provide formulas for you. Okay, it takes people years, many PhD lessons, courses to develop that. We are the lucky ones who just use it. Just like what we did before, we take some integrations, derivatives, we get this term. This is your strain displacement matrix. Any questions so far? So what we did, we define the elements with 3 coordinates. We developed the shape function painfully, okay? Many terms, many calculations. So we need an Excel spreadsheet. We need some program, computers to help us. We have the shape function. and then we take the derivative of that. I forgot how many times, you know. Then we have a 3x6 matrix, which is a string displacement matrix. Sub everything back to the total potential energy equations. Remember, the stiffness is DED. Okay, however, how we define it, the DED is very different from what we had before. The elasticity is not one term anymore. For 2D elements, the elasticity is still a constant, but it's a 3x3 matrix. It's 3x3. It's not a single term anymore. It's not constant. It is constant, but it's not 3x3. So we have D, we have E, and we have D. Then we calculate the stiffness matrix for the 2D elements. Now I have a question for you. What's the size of that stiffness matrix? The 2D element stiffness matrix, what is it?
6
Size?
by 6.
6x6. If I merge two 2D elements together, very likely what, okay, this is one element, right? If I have two 2D elements times 2, what's the size of this matrix?
8 by 8.
Correct. Okay. Because each element has 6 degrees of freedom, but these elements also have 6 degrees of freedom. However, we are sharing 2 nodes for both of them. They share 2 nodes, so they share 4 degrees of freedom. Okay, so because they share 4 degrees of freedom, so it becomes 6 degrees of freedom plus 2 more. And also you can find out the degrees of freedom by counting how many nodes in total. Each node has 2 DOF, right? Each node move X and Y. So 4 nodes, 8 by 8. Any questions? Let's move on and do an example.
So for the 2D element,
Yeah, sure.
we assume that all the nodes will have 2 degrees of freedom, right? Just like the beam element where we have like up and down and then the turning, something like that.
Correct. Yes.
So for 2D element, always 2 degrees of freedom for all the nodes.
Right. It doesn't turn. It only moves up and down. Okay, you know what? Somehow the node of the 2D elements, the movement is exactly same as the truss element.
Yeah, it looked pretty similar. That's why I was gonna ask.
Yes, they are exactly the same. You know, okay. So that's my hints right here. If I have a truss element, okay, and then I have a 2D element. Guess what? Because they have the same degrees of freedom, I can merge them together. We only combine 2 different types of elements when they have the same degrees of freedom. That makes sense though, right? Because when that node move, it communicates information to this guy and that guy. And because this node move, it will affect this node. So it will affect the movement of this element as well. I assume this is fixed, right? So watch out, man. You might see something like that in the final exam. I know. Yeah, you guys are hating me now. All right, let's do some example.
Before we move on,
Yep.
would it be possible for you to just give us maybe upload a tutorial on how to design the Excel for getting the area and then solving those matrix upstairs for the when you said the displacement matrix where you need the Excel spreadsheet?
Okay, I will give you a tutorial, but I want you to try it first. But not today, because from today to next week, focus and study your midterm exam. And after the midterm exam, the week after, we will spend more time on 2D elements. Answers, you know what, maybe that's my plan. I haven't finalized it yet. I want to probably after the midterm, do another lesson, another lecture on the theory stuff, like thermal and vibration stuff. And then I'll just finish all the lectures and let you guys focus on answers, finish it off, and then maybe take a day or two off, like no class, and you guys just work on answers or so. But I promise, yeah, I will give you some tutorial how to design the Excel spreadsheet. But don't just wait for me. Start ahead. Excel is a very good tool. Okay, I'm working right now. I still use Excel every day, rather than like some other fancy software. It's like Excel, just doing a lot of calculations. The Excels can do matrix multiplication as well. Okay, Excel can inverse a matrix. Try it out. And yeah, if you study these notes right here, the Excel spreadsheet is not so fancy. You just type in the coordinates. Okay, you will get, because every single term, the delta, beta, alpha, is all constructed by the coordinates of the triangle. You know what? Guess what? Let's do one example. I'll show you what I mean. Okay, so we have the strain displacement matrix. We know the stiffness matrix of this. Okay, there's examples right here. I have a wedge. I have a solid. Note, this is a solid 2D plate. I will identify that. Usually in any problems that I have, I will either tell you it's a 2D solid plate, or I'll draw some thickness to it. Okay. Anyways, it will be well specified in the question. Okay. That plate is totally glued or constrained along the wall. Okay, the whole side is attached to the wall. No movement at all. The height of that thing is 10 inches. It's sticking out by 20 inch. Okay. At the tip of the corner, it has a down force by 5,000 pounds. Okay. This is the elasticity. It's a 30 times to the 6 psi elasticity. The thickness, T is a thickness. It's 1 inch, 1 inch thick. Poisson ratio is 0.3. That's usually regular Poisson ratios for metal. Okay. For wood is something different. I forgot what is it. Okay. Glass, pretty much it doesn't compress or getting thinner. You just break apart. Okay. But anyways, all the information will be specified in the questions. The question is how much it deformed. How much deformed? Okay, what's the first step? When we see the problem like that, the first step is name them, give them note. Okay, this is an element, one element. Well, because this, right, in this case, there's only one element. So I don't have to say, oh, this is element number 1. Nah, because, save some time. If we have more than one element, then we name them. Okay. The next step, name the node. So 1, 2, 3. What if I don't like it? I want to have node 1 here, node 3 here, node 2 here. It's totally fine. Okay. The solution is not depending on how you name the node. As long as you're consistent, okay? As long as you're consistent, you get the same result. Okay. Well, so you name the node, okay? And then you design the coordinate, which is extremely important, okay? In 2D elements, you need to define some coordinate, okay? I like zeros. Okay, well, that's why I started in 0, 0. But what if I like to challenge myself? You know, I like to start this node by 2, 2, and then 10" up is 2, 10. And then up there, I want to challenge myself. This will be a 22 and 10. Totally fine. You can do that as well. Okay. But I think you are crazy though, you know, if you do that. The simplest way is start from 0, 0, okay? And then just name your coordinates, name the address according to the dimension given in the question. Okay, sorry, I heard some questions. What is it?
Yeah, Chris, you just erased that. But when you wrote 2, 2 on node 1, and then on the second one you wrote 2, 10, it should have been 2, 12, right? If that's what we're looking at. If you start from 2, 2, this should have been 2, 12 because this is 10 plus you already had 2, right?
Perfect. See, that's what I meant. You start from 0, 0, less mistake, much easier, you know. But I'm just saying that if you write 2, 2, you may write 2, 2, but this is crazy, you know. Just start with something simple, and then less mistake, less risk, and then so much easier. Okay, where were we? Okay, we have the elements, we name the node 1, 2, 3, and then we assign some address, assign some coordinates. You know, we tell the program where it is. Okay. The next step, okay, because it's gonna be a messy. Okay, so this is, I know what I taught you before is look for the K matrix, stiffness matrix, then look for the displacement vector or something. But sometimes it's easier to visualize the problem by defining the displacement matrix and the force vector. Sorry, displacement vector and force vector. Because I can totally understand the problem and I can reduce the matrix beforehand. So in this case, this is what I did. I defined this displacement matrix, that displacement vector, and then I defined the force vector, okay, U1, V1, okay, and then I just start canceling things out. You know, I know node 1 and 2 is total attached to the wall, so it's not moving at all. 0, 0, 0, 0. So because the right side is 0, very often the left side is an unknown. Oops, the left side is an unknown. Okay, now let's see. Node 2 and node 3. So UV and U3 and V3 is allowed to move. So let's look at the applied force. So node 3 along the y-axis is negative. Remember, sine is everything. Eh? It's going down by 5,000 pounds. Okay, there isn't any force. There's nothing. I didn't write like 20 pounds. I didn't write that. Eh? So it's no force in it. Not any apply force on the x-axis on the node 3. So I named 0. Now the next step for any 2D elements, okay, you need to assemble a little table which tells you the node number and where it's located. Okay, Note 1 is 0, 0. Note 2 is 0, 10. And note 3 is 20, 10. Try to stick with a 0, 0. Yeah, you may do this, but again, it's just easy to make mistake by those things. The area, I didn't use the formula. I didn't use the formula there. 2a. You are allowed to. You are allowed to do the. Yes, you are allowed to just calculate area of the triangle like this. Okay, the next step. Alpha 1 is, what is alpha 1? Back to it. Alpha 1 is okay, in this case, J is 2, Y is, K is 3, K is 3, and then J is 2. So alpha 1 equal to X, oh my God, X2 times Y3 minus X3 times YJ. That's it. X2 or whatever. Alpha 1 is a X2 Y3 X3 times Y2. Is that right? Did I make a mistake? Okay. X2 is 0 times Y3 is 10. And then X3 is 20 times Y2 is 10. So 0 minus 20 times 10, which is a negative 20, negative 200. Okay, let's do beta. Let's do this one. Beta 1 is, okay, according to formula is Y2 minus Y3. Okay, it's Y2 is a, hold on. Did I do it right? Y2, what is Y2? Y2 is 10. Y3 is 10. Okay, I got it. Yeah, 0. Okay, and then you repeat the same thing 9 times. See, that's why it is so painful to do it by hands. It takes patience, and it's very easy to create error. So that's why it's more reason to in an Excel spreadsheet, you define the 3 coordinate set, and then boom, within 1 second, less than that maybe, it gives you all the alpha, beta, and delta. And with that information, you get what? You get a D matrix, because the D matrix is all constructed by the alpha, beta, and delta. Okay, I said that earlier. Where is it? Where did it go? It's right here. See, with the 9 terms, alpha ijk, beta ijk, and then delta ijk, you get the displacement matrix. Okay, and then with the elasticity box, you got a 6 by 3, 3 by 3, and then 3 by 6. Okay, this is the D matrix, elasticity matrix, and the D matrix, I think this is, I forgot, this is, yeah, that's right, that's a transport. Yeah. Look, in this equation, in this problem, right, I do everything by hand, okay? But you are allowed to do that in Excel. Okay. Now, finally, we get this.
We
Yes.
can develop this a final K matrix in Excel. That's what you say.
Oh yeah, I encourage it because it's so easy to make mistake by hands. Okay, your calculators. Then how you do so? Okay, after the midterm, you do some research online. You know how to do matrix operations in Excel.
I see there is an example in the book. They went from step by step. how to-
Okay, you may try it.
I think
Okay,
that
and
was for
if you're confused or something, I promise after the midterm exam, I will show you how to do it. You know, but for this week, study your midterm first, and after midterm, you do some research on things, and I'll go through it the class in a class after. Okay. So that's the big ugly 6x6 matrix, and I rewrite the displacement vector from before. Because there are a lot of zeros there, right? So I just focus on the last two equations. I'm not ignoring the previous four, but because this is zero, right? I just look after the two unknowns and two equations. And then we find out the displacement. Okay, somehow that node is not moving in an x direction at all. It only goes down by negative 1.733 inches. Questions? Okay,
Oh,
do
what's
not,
V?
okay. Huh?
It says V is 0.3. What does that represent?
The Poisson ratio. It's not a V. It's something different, but we're out of alphabet, you know? So it's a Greek letter. Okay. This is the ratio to measure how much when that's the little thing that you talk about. It's not really a V. I forgot what is the name of that thingy. Okay,
Lambda?
but it,
Lambda?
lambda. Okay, thank you. The lambda tells you
I'm just guessing. I don't know.
it's good enough. You know, let's call it lambda for today. You know, I'll find out the real name. But the lambda, okay, it measure how much it deform in the when you squeeze something. When you squeeze something, how much it deform in the lateral directions. Okay.
But as far as I know, we haven't used that in our calculations, did we?
We haven't, we did. It is within the E matrix. It's right here. That's the lambda. And then I specify that in the, yeah, that's right. Look, right here. See, we use lambda. Okay. The lambda is required in your elasticity matrix.
Oh yeah, because E is not a constant anymore. It is still, but
Well,
in this form.
E is a constant, but it's a 3x3 ugly matrix. Okay.
Pretty sure that V is new. Lambda's upside down.
Thank you. Okay. Thank you. All right. That's it for 2D elements for today. Yeah. I know it's kind of rushed, but I'll do more examples in the future. But guess what? Next week is a big deal. Your midterm test worth 20%, you know, and so it's quite expensive, you know, and well, too bad it's only 30 of you show up. You know, I have 45 person in my class, you know. Anyways, let's do some review, okay?
Professor, do we need to know how to get the inverse in midterm? Like in most of these stiffness matrix derivations, we did the inverse. Like I tried doing it, but it's pretty hard.
It's up to you how you define. And anyways, I'll go through that. Okay, I promise. Okay, we'll explain inverse and then degrees of freedom in each tab. Okay, so far we've gone through a lot. Okay, in a week number 1, I tell you why we study FEA, because we want to save money, save time, and save life. Okay, is before we have FEA, everything's rely on testing. Okay, lots of people get hurt, you know, and expensive to do so. So the most simple element is the rod element, and the strength, the stiffness of the rod elements is defined by the cross section, elastic, the materials, what elasticity it has, and the length of it. And the spring elements or rod elements has 2 degrees of freedom. That note only moving along the x-axis or y-axis only. Okay, so that thing is allowed to move left or right. That note's allowed to move left or right. Rod elements has 2 degrees of freedom, and the stiffness matrix for the rod elements is 1, 1, negative 1, 1, 1, and negative 1, negative 1. Okay, I sent you a little gift this morning. It's a formula sheet. Did you get it, guys?
Yes.
Yeah,
Yeah.
I received an email, but haven't had a
Ki-
chance to check it.
Never mind, you know, it's just a formula sheet for, okay, well, my midterm is an open book. Well, you know what, we are distant learning. I don't know what you do, you know, I have no control over that. But even though in our in-person class or the exam or midterm is open book, okay, and instead of flipping through all your notes, I'm a nice guy, man. I give you a formula sheet, so you just use that sheet and just do the work on the problem. By the way, one thing though, I encourage teamwork for your quizzes, for your labs. However, midterm exam, again, I have no clue what you do. Please work on your own for your own benefits, okay? Okay, that's all my suggestion. I really hope you work on stuff by yourself. Absolutely no teamwork in a midterm and final exam, please. Okay, so that's the stiffness matrix for rod elements, 1, 1, negative 1, negative 1, and then how we merge them together. You should be very, very comfortable with it now, okay? How you merge them, these 2 elements together. Then the week after, okay, we talk about the truss element. Everything stayed the same except the spring elements is elevated by some angles, okay? Because it's elevated, it's slanted, right? So we have to define the movement by each node in 2 directions, X and Y, X and Y. So that's why the truss element has 4 degrees of freedom. That's the truss element, has 4 degrees of freedom, okay? And because the truss element has 4 degrees of freedom, the matrix is also 4 by 4. Okay, it's a 4 by 4 stiffness matrix. And how you define the stiffness matrix for the truss element is included in your formula sheet. You know, before we do so, we need an information table. It tells you the angle. What's the code? Okay, let's do one example. Before we move on, write the equations. We need an information table, tells you the cosine and sine. Okay, and then we find out what is a cosine square, s square, and we can, with that information, we can construct the stiffness matrix. And after we merge the global stiffness matrix, we apply the boundary condition. Okay, we lock them And when we log something, the 6x6 matrix is down to 2 only, okay? Which is a lot better for calculations. Okay, with that information, we can, with the two equations that we solve, we find out the displacement of a u1x and u1y. We evaluate all the axial forces. And with that force, we draw the free body diagram, and we can find out the axial load on each rod. Okay. Yep, which is also covered in the quiz 2. Yep. Okay, that lecture, we just do more examples on rod elements, okay? Right here, it's just one element, okay? Right here has 4 elements, but they're all the same, so we add them together, okay? It becomes a bigger matrix, but look at that, 4 elements, because there's similarity, we combine them together, because they're all rod elements, right? I combine them together, become a bigger K. That one is an interesting problem as well. It's a mass of string elements all merged together. But again, when they have the common degrees of freedom, you can combine them together easily. Okay. And where you locate them depends on the node. Okay. Which is the node. Okay. You guys are doing well in that quiz. Yeah. Okay. This is one more example on a truss element. Okay. That's pretty straightforward. If you can do quiz 2, this is not a problem at all. Okay, minimum potential energy is a lot of theory stuff. Okay, basically this is approach on development of matrix. Approach to development elements. Okay, the first step, always look for the shape function, and then we develop the okay, that's an energy equation, but I'm looking for the string displacement matrix. That's right. From the shape function, then we develop the string displacement matrix. And with the string displacement matrix, we can calculate the stiffness matrix. That's right, here you go. Look at that. With all the math that we've gone through, we're back to square one. Okay, one for rod elements. Okay, this is examples on potential energies. Okay, check this out. Okay, the stiffness matrix stay the same because it's a rod element, right? It's spring element. The applied force is different. We need to use the shape function. Shape function of it. Okay, we need to take the integration of the shape function, and it has a very special applied force due to that integration. Okay, I have that in the formula sheet as well. And then this is equivalent to your quiz 3, so it should be good. Okay, beam elements. Okay, this is your new friend.
I have a question regarding quiz 3.
Yep.
We have a force in terms of x, right? So when we are evaluating the element 2, so why aren't we taking into account the force that's accumulated from element 1 to when going to element 2?
Okay, I'll get to quiz 3 in this tab. Okay.
Okay.
I'll tell you more about it. Okay. Let's carry on with a beam elements. Okay. The beam elements has 2 nodes, but each node moves differently. The node only goes up and down. Okay. I mean, which is I would say, I shouldn't say up and down. The node moving normal to the element. Okay, it's 90 degrees to the element, and each node can turn as well. So right here is a beam element has 4 degrees of freedom because each node move in 2 ways. Same thing, we need to develop the shape function. And then according to the band theory and also string energy theory, we develop the string displacement matrix. Then we calculate this, the stiffness matrix. Okay, I will not ask you to develop it for me. Again, use the formula sheet, calculate the stiffness matrix for me. And then the work done, okay? There's a uniform load. Let's say there's a uniform load on the beam elements, right? The load is applied by this. Again, you don't have to develop it for me. Just use the equations in the formula sheet. Here's an example for it. You know, we applied a uniform load on the beam element, which is this. Okay, all the equations are given. Okay, and then you find out the notes how much it deflect.
Chris.
Yep. What's up?
I think I was a little confused. So for the applied for the force matrix for the beam,
Yep.
is the WL over 2 and WL squared over 12, is that apply for just an applied force as well?
This
Like,
is only the whole mess right here. Okay, is the uniform load px 100 Newton meters only. All 4 terms is represented by the uniform load attached to it only. If there's an additional load, let's say 100 pounds, right? This is something extra. Okay, this morning I sent you 2 gifts, one formula sheet and one other problem on the on exactly what you just said. Okay, I will help you with the truck before we finish today's class. Okay, I sent you 2 things, right? The formula sheet and a truck on beam problem. Okay.
Actually, in our quiz 4, this was also a similar case where we had an external force at the end of the node.
Yep, that's right. Okay, the truck on beam problem that I sent you this morning will explain everything. Okay, I'll go through that with you very soon. Okay, the next tab is nothing fancy. We just reviewed quiz 1. You should be very good at that now. There's a few more notes. Hold on. You had that more example on beam elements. Okay, we merge 2 beams together. That's what we sum up. Again, truck on beam problem, we'll go through that. We'll go through that. Pre-job brief on quiz 4. Okay, that's very straightforward. We identify 2 elements here. The first part is beam element, and then we use the formula sheet to construct the stiffness matrix, and then we use the formula sheet to construct the truss element matrix. We combine them together with the similar degrees of freedom, and we solve for it.
Chris, can I ask a question?
Yeah, sure. What is it?
The point load that we applied on the second node, do we divide it between the beam and the truss, or we just give it to the beam? The 100 pound on 0.2.
Okay, good question. 100 pounds, 1,000 pounds on it, right?
Yeah.
Who took it? It is being shared by the, that element, that 1,000 pounds is being shared by the beam and the truss. How much is taken by each? We don't know. We let the matrix decide it. All we did is just, what is the this is a F1 in the X direction, moment. Sorry, man. F1 doesn't have X, okay? F1 only have Y. And then we have moment 1. Can F2 for the beam elements only have Y, okay? And then it has moment 2. And then U2, which is a F2, I think it has an X now because it's a truss element. It has an X. And then U3 is a F3X, F3Y. Right here in this case, we just say apply force. Oh, I cannot erase that. It's not, it's wrong. We have apply force by the uniform load, right? And it has an additional force of a 1,000 pounds downward. So, which is minus 1,000. Okay. And then I just apply 1,000 pound right here. That's the beauty of FEA. Who is taking what? Okay. It's a teamwork between the beam elements and the teamwork between the beam elements and the truss elements. Oh, truss elements is like this. Oops. Boom. You get it? So this 4 terms is all the applied force on the beam elements. And this 4 terms is the truss element. So when I say 1,000 minus 1,000, right? Who's taking what? I don't know. But I just understand it's teamwork. They both sharing some force, okay? And they must work together because we combine them in a huge 7x7 matrix.
Yeah, so as long as it makes to the global matrix, then it should.
That's
be
right.
okay.
Don't think too much. You just say globally. You know, I have a 1,000 force, 1,000 pound down. Okay, I will tell you more about it in the truck on beam problem. Okay, I want to.
Chris,
Yes.
one.
What,
So
what,
in the same quiz we were looking at, can there ever be a U1 in quiz 4?
Okay, first of all, how you name it? Where's U1?
Node 1.
Node 1. Okay, Node 1 is totally belonged to the beam element only, and the beam elements doesn't have U. It's only V. It's only right.
True,
Okay,
true.
true. However, this node has a U. Why is that? Because it's shared by the truss element. Okay, so that is why this node is so funny. It has 3 degrees of freedom. It's two given by the beam elements, 2 degrees of, okay. This node, okay, node 1 only has 2 degrees of freedom because it's beam only. Node 2 has 3 degrees of freedom because it's 2 contributed by beam elements and 2 degrees of freedom contributed by truss elements. However, they have 1 common degrees of freedom, so they share the same V, share the same V2. So that's why this node is so funny, it has 3 degrees of freedom. And then node 3 has 2 degrees of freedom only because it's only detect or work with truss elements. So it has 2 degrees of freedom.
Chris, can I ask one more question?
What is it?
On node number 3, it's a truss element and it's like a pin, right? So why do we say that it's free to move on the horizontal direction?
It's not free to move. I cancel them. U3, V3 is 0. Look, U3, V3 is all 0.
Okay.
It has the degrees of freedom, but due to the boundary condition, I lock them.
Okay, thanks.
It's allowed to move in theory, it's allowed to move, but because of the boundary conditions, I lock them. And I love zeros. You know, you reduce the matrix.
Hi, sir. Here in the end, we end up with the unknown three equation. Can we use the Excel sheet to solve these?
You may, but show me your work. Because if you
Excel
don't show, okay, you screen grab something or whatever, you know,
Yeah,
attach.
for the quiz I did with the Excel, so I attached the Excel output.
No, don't do that. You know, I'm not gonna open
like
in
in
a
PDF format.
okay, what you did is a screen grab that little box and show me you inverse that, and then you get the result. Okay, because if the final answer is wrong, you lose everything. But if you show me some steps,
there are some calculator you can input the numbers, and for the three equation they give you the final answer also.
Oh, again, okay, you know what? It's up to you how you do it. But the risk is, because if you show, okay, let's say, okay, here's why. Okay, the equations. Okay, when you solve the final like three equations, three unknowns. Okay, if you show me the work, okay, the total process, I would say the three equations, three unknowns, is worth about 10% of the total score, right? If you show me the work, and then the answer is right, you get the whole 10% of it. But if you show me the work and you get a wrong answer, I can say, well, you still get 5%. But if you don't show me any work, you say, okay, I calculate everything by a fancy calculator, a fancy app in my smartphone. And if the final answer is wrong, you lost all 10%. You know what I mean? Because I have nothing to evaluate, nothing to base on. You just say, I have a fancy app to calculate a matrix for me. And then the final answer is wrong, you lose all 10%. But if you have some work, you show me a matrix, okay, by the way, this is a screen grab of my calculations, okay? If the final, yeah.
The wrong final answer will be a result of a wrong equation development instead of a mistake in the calculation.
Again, this is so important. Show me the process. Okay. Let's say I hire you to analyze a bridge for me. Okay. 2 weeks later, you give me a statement, Chris, the bridge will work. It passed. Just one line. And you charge me 20 grand for the analysis. Okay, thank you. No, you show me step by step. This is the elements I use. This is the applied force, the traffic on the bridge. And based on this analysis, okay, here's my equations. Okay, and then I will, because of my assumption right here, all the step or the process, yes, your bridge will work. Then you know what? I'm with a 20 pages report. Then I'll pay you 20 grand happily, right? Yeah, again, it's your choice, but again, the equations, yeah.
Certain way, and I'd love to have your feedback on it. So yeah, like if you think it's okay, then yeah, I'll do it same way in the exam. But if you think it's not okay, then yeah, I'll change it.
I'm very flexible, you know, how you calculate the equation. Well, by the way, okay, you must show me the boundary conditions, how you assemble the global matrix, because those things worth a lot, okay? With how you assume the elements, note, how you construct them, how you build your model, it's worth like 80–90% of the total thing. How you solve it, the equation, what row reductions, you know, inverse matrix or whatever fancy app, you know, it's up to you. But the total, that process worth about 10% of it, of the total score. Okay. And then like if the final, you know what, try in the midterm, you know, then I'll give you some feedback. I saw there's a chat. Can you post me some midterm examples online? Hey, buddy, truck on beam is coming up. Okay. Hang on, let me see. Where will we? Oh, there is some questions on a quiz 3. Okay, quiz 3, nothing fancy. this is the stiffness matrix. This is a rod element, 1 by 1, and then we take the integrations of it. We need a shape function for the rod elements. Okay, and then we take the integration of it. Remember the tricky thing is the first force is going from 0 to 30. The second force is from 30 to 60. Once we take the integrations and we merge them together, this is the first force vector, and this is the second force vector. And we add a reaction force to the end of it because it's attaching to the wall, right? And then we calculate that. Okay. Again, how you solve the equations is about 20%, 10 to 20% of it. Okay. If you just show me this without that, without the process, okay. If the answer is right, I still give you the mark. Okay, but if it's wrong, I cannot give you any partial marks on it. So there was some question on quiz 3, right? Now's the time. What is it? Did someone ask me quiz 3?
Element 2, can you go up?
Elements 2, yeah.
Yeah, so when we consider the applied force, don't we have to consider you divide it and you fix it also on a U2. So don't we have to consider the force applied from force accumulated from U1 to U2 in terms of X also there?
Okay. When we calculate the individual force by each element, we don't combine them. We just go with 4,500 and then for the next element, we deal with this one only.
Not here, I'm talking about the PX where you
PX.
Like this is quiz 2 part first. I was like, my question is really on
that's quiz 3. Quiz 3.
Yeah, quiz 3 part first. Yeah, my question was really on, I think, part 2, where we have the load in terms of X, something like that. Let me check. My God, I'm sorry.
Hey, how about this? You know what? You can email a question to me because I don't.
Yeah, part
really
2, where we have the gradually increasing load instead of.
Oh.
Yeah.
Okay, nothing fancy. Only the integration is harder. Okay.
Yeah,
instead
harder,
of.
But for element 2, what I did, instead of just keeping it 10x, I did 300 plus 10x for element 2 because I thought
Why did you do that?
Because I thought the first part was also acting.
No. The first part and second part is totally independent. Do not do that. Okay. Right here, the integration is only 300, right? The first part. The second part, the integration is 10x. Don't add them together. Why? No, there's 2 different problems. Okay. Do not add them because I didn't ask you to. Okay. Anyways, if you have more questions, email it to me. Now, okay, this morning, I send you another example for you to practice. Okay, this is from one of the previous midterm exam that I let you try on. You know what? I want you to try on this. You know, let's take a short break. Oh well, it's a break for me, but it's not a break for you. I will go through that at 10:30. Okay. Well, if you cannot, well, for 15 minutes, right? You cannot finish the whole thing, but at least tell me the plan. How do you translate everything into elements and notes? Show me the pre-processing phase of the FEA, okay? And I'll help you to go through that by 10:30. Is that cool? Yeah, let's take a short break. Thank you.